Let's look at the derivative of f with respect to time. To get L of this function, of course, we multiply by e to the minus st, integrate from 0 to infinity with respect to time. So we're going to use integration by parts. We have a product of functions here. We're going to let u equal e to the power of minus s times t. dv then is the rest of this integral. If u equals e to the minus s times t, when we differentiate this using the chain rule, when we differentiate e to the power of something, we get back that exponential, but we must multiply then by the derivative of the power. Differentiating this with respect to time, we get minus s. Then we can multiply both sides by dt, so there's du. Here is dv. df dt times dt just gives us df. So dv equals df, that means v equals the integral of df, which is f. So here is u times v. Now let's take the upper limit. Let t tend towards infinity for this product here. Now we are assuming that e to the minus st dominates, so this will go to 0 faster than f of t will go to infinity. Assuming that f of t does go to infinity, it may not, but if it does, then we must have the situation that e to the minus st goes to 0 faster, so the entire product becomes 0. Then we have a minus sign and we plug in the lower limit, so if we plug 0 in for t, we'll get e to the 0, which is 1, and then we have f of 0, so we just have 1 times f of 0. Now in this integral we need to multiply v by du. Well, v is just f of t, that's v, and du is minus s e to the minus st times dt. Now we're integrating with respect to time, of course, so s can be considered a constant here. We can take it outside the integral sign, so we get minus minus or plus s. But notice now that we get this integral here that we've seen before. This is just a definition of the Laplace transform of f of t. So this is what we get, minus f of 0 plus s times L of little f of t, and the notation for that is big F of s. This is a function of s, of course. Let's look at this example here. Let's suppose that little f of t is sine of t times u of t. To get L of that, we can look at this table. So we look at rule 5 here, and a is equal to 1 here, so we plug 1 in for a, so we 1 over s squared plus 1 squared. So we call that big F of s. Now let's consider the derivative of little f of t. So we have to differentiate sine of t times u of t with respect to t. Well, the derivative of sine of t is cos of t. Actually, the derivative of all of this is cos of t times u of t, because for negative values of t this is 0, u of t is 0, and if we differentiate 0 with respect to time, we just get 0, of course. So just to see the picture again, f of t is 0 for values of t less than 0. Of course, if we differentiate this, we just get 0. It's just a horizontal line. Its derivative is 0. So in general, the derivative of a causal function is another causal function. Now we can use our rule to get L of cos of t. We want L of df dt, the derivative of sine of t. Well, we know it's minus f of 0 plus s times big F of s. Well, what's little f of 0? Well, that's just the sine of 0, which is 0. And we have to multiply s by big F of s. Well, here's big F of s. So we get s over s squared plus 1. And that's what we have here from this table. If we replace a with 1, the Laplace transform of cos of t is s over s squared plus 1 squared. Let's get the Laplace transform of the second derivative of f with respect to time. So we apply the definition, we multiply by e to the minus st and integrate with respect to t from 0 to infinity. I will let u equal e to the minus st. So differentiating this, as we've seen, we get minus s e to the minus st times dt. So that's du. Here's dv, so we need to integrate the second derivative of f with respect to time. Well, that's just going to give us the first derivative of f with respect to time. So we multiply u by v and evaluate with the limits 0 to infinity. Then we've minus integral of v times du. V is dfdt and here is du. We can take this minus s out. Let's look at this at the upper limit, plus infinity. If we let t tend towards plus infinity for this product, as I've said before, e to the minus st usually is meant to dominate, so that will go to 0. Whereas this here, well, whatever it does, e to the minus st will go to 0 faster than, say, this if it goes to infinity. So we'll get 0 here. Then we've minus this thing evaluated at 0. Well, if we plug 0 in here, we get e to the power of 0, which is 1. And we have to evaluate df dt at 0. Now, notice this integral here. This is just the definition of the Laplace transform of this function, df dt. We've already gotten this thing here, L of df dt. Here it is, so I'm just plugging it in here. Multiplying s in here, I'll write this term down first. We get minus s times little f is 0. I'll write this term second, minus df dt at 0. And then we have s times s, that's s squared times big F of s. We can write df dt as f prime. So df dt at 0 is f prime of 0. Here we see that a function little f of t satisfies this differential equation with initial conditions f of 0 equals 1, f prime of 0 equals 0. And we are going to get an expression for big F of s. To do that, we are going to take the Laplace transform of each term in this differential equation. Let's look at L of 3 times t. Well, by linearity we can pull out the 3, so we're getting L of t, and we can use this rule here with n equal to 1. So we get t to the 1, and its transform is 1 factorial over s to the power of 1 plus 1. Well, that's just 1 over s squared, so we end up with 3 over s squared. As for the derivatives, well, we've already had these two rules. We just need to evaluate little f of 0 and little f prime of 0. Well, we don't have to evaluate them, of course, we're actually given them. Little f of 0 is 1 and little f prime of 0 is 0. So we plug 1 in here and 0 here and 1 here. So we get these results. Now we can plug what we've got into this differential equation. So here is the differential equation. So we've taken the Laplace transform of both sides, and we're using the linearity property, if you like. So L of this difference is the difference of these transforms, and we've L of 3 times t on the right hand side. And filling in, we have this here. We just have to make f of s the subject. So next we divide across here by s squared minus s. We can multiply above and below here by s squared. So on top we'll get 3 plus s cubed minus s squared, and multiplying s squared in here we get s to the 4 minus s to the 3. Well, we can factorize s cubed out of the denominator, and you see we get s cubed minus s squared plus 3 over s cubed into s minus 1.